Okay, so here we're going to introduce here working with the combinatorial proofs. Right, so there are ways here to prove quantity. So, for example, let's take a look at Pascal's identity, which states that n choose k is equal to n minus 1, k minus 1. n minus 1 choose k minus 1 plus n minus 1 choose k. Okay, and one approach to do this is to strictly doing algebraically. Now, before we get into that, just a reminder, when we have something like 5 factorial, that's 5 times 4 factorial, which is equal to 5 times 4 times 3 factorial, etc., right? And in general, if you have something like n factorial, that's n minus 1, n times n minus 1 factorial, or n minus 1, n minus 2 factorial, etc. So you get down to 3, 2, 1, etc. Right? You just keep going, and even more generally, n minus k factorial, that's n minus k times n minus k minus 1 factorial. All right, and then n minus k minus 2, etc. Right? You keep working your way down there. Okay, so I bring this up because just remembering that is going to come in handy as I work through the algebraic proof here. All right, so if we start with the right-hand side here, right, there's more to work with here, right? If you have n minus 1, choose k minus 1, plus n minus 1, choose k. Here, all right, so I can start by kind of expanding here, and we have n minus 1 factorial over n minus k factorial and k minus 1 factorial. Okay, when you subtract n minus 1 minus k minus 1, those ones cancel out, so you're just left with n minus k factorial. And on the other end, you have plus n minus 1 factorial over k factorial, and then n minus 1 minus k factorial. Excuse me. Okay, now from here, I'm going to combine these by coming up with a common denominator. So I'll do that here on the term on the right here. I'm going to multiply the numerator by k and this by k. All right, now the reason for doing that is now k times k minus 1 factorial together leaves me with n minus k factorial, and then this quantity here, that just becomes k factorial, right? Because my expansion up there, right? Now, on this end here, what I'm going to do is I'm going to multiply the numerator and the denominator here by n minus k. All right, and now what we have here and here is that same quantity that we see here. All right, so both of those together turn into n minus k factorial. Okay, and excuse me, up here we're left with k, and then over here we'll have n minus 1 factorial, and then n minus k. Okay, now we can, again, this is all just algebraic work, right? From here, I'm going to write these under one denominator since now it's common. So k factorial, n minus k factorial, and then up here, right, they have a common factor of n minus 1 factorial. So I'll factor that out, and we're left with k plus n minus k. And then we see here, all right, well, now those k's cancel. And then we're left with n minus 1 factorial times n over k factorial, n minus k. But again, here, what do we know about this quantity here? I can not expand it, but compress it into simply n factorial, k factorial, n minus k factorial, and that is n choose k, which completes the proof, right? Nothing wrong with the proof, right? The only problem here is that I'm not interested in just showing the proof here. I want to understand what it's telling me, right? A lot of these counting problems can be quite challenging, and if we have a formula, but how do I interpret that formula in terms of my counting problems? All right, so we're going to take a different approach here. While this is true, right, it does lead us to the correct answer. We know at least, all right, like algebraically it works, but if I'm coming up with a counting problem, right, how do I know when to use it? Okay, so the idea here is that if we have two expressions that count the same set, they must be equal, right? That's the approach that I want to take here, right? That if we have two expressions and they count the same thing, both count the same set, both count the same set, they must be equal. Okay. All right, so as we approach these combinatorial types proofs, what we're going to be looking for is find a counting question whose answer is related to the identity, right? You answer the question one way to get A, to get one of the expressions, right? And then answer the question a second way, right, to get the other side of the expression here, right? So what we're going to introduce are counting arguments. So no algebra, right? So let's take a look. We'll build to this Pascal's identity. Let's look at a simpler identity here. So prove n choose k is equal to n over n minus k. Okay. All right, so now let's relate this to a counting question, right? So the question is, how many k element subsets are there of a set with n elements? Okay, so that is the counting question that I'm set to ask here. All right. So the first answer is our left side of the equation here is, so answer number one is choose which k elements to include. All right, and that is our n choose k, right? That's what that number gives us. All right, so that was something that we have done before, right? That's how we approach those problems. Now, what if I take a look at it a different way, right? How do I relate that to that other side of the equation here? All right, so instead of that, all right, instead of choosing k, what if I look at the other side of the problem here? So instead, choose which n minus k elements to exclude. Okay. And that's for that n minus k, right? Think of, we have n is 10, right? So there's 10 elements, and you want subsets of size 3, where you're excluding 7 of them, right? And what this statement is saying, well, what if I count the ways to exclude them? All right, so they're the ones that are outside, and that's equivalent to counting the ones that are inside, right? So if we choose which nk elements to exclude, well, that is n, choose n minus k, right? Both answers count the same subset. They just take a different approach to getting there, right? So they count the same subsets. So if they're counting the same subsets, my combinatorial proof means that, well, if I take this approach, then it has to be true, since they are counting the same thing. I just take a look at it from a different perspective, right? And that is the proof. I know algebra needed to show this, right? But it's more of a counting argument so that we know what we're counting, and we're counting it in two different ways, right? You can also think of it in the bit string problem, where we counted the weight of the number of ones, but if we know the length of the string and the weight, we can also count, right, the zeros, right? You essentially flip the what the zeros and the ones, how we count them, right? Usually we focus on the ones, but now what if we focus on the zeros instead of the ones? Right, and that's the same idea here. All right. Okay. Now, a second question we can ask here is, so we want to prove that n choose 0 plus n choose 1 plus n choose 2 all the way up to n choose n is equal to 2 to the n. Okay, now again, what's going to come in handy here, what we want to do is find an appropriate counting question. All right, so the counting question here is how many subsets does a set with n elements have? Okay, and here we could see that on the right side of the equal, we could say, all right, well, n is the total number of elements, and we break it down into the size of the subsets, all right? Size 0, right? The empty set is a subset of every set, right? Size 0, size 1, size 2, etc., all the way till we get to of size n. You include all the elements there. All right, so here, group subsets by size. All right, and then that gets us here n choose 0 plus n choose 1, etc., until we get to n choose n. Right, and that'll get us the correct answer, right? There's a lot of, in practicality, there's a lot of calculations that are needed there, but that's how we would do it. All right, now answer 2. All right, now this is a more streamlined approach, which is a nice way to think of this. For each element, independently decide in or out. 2 choices each, right? So here, each element it's in or out. Okay, so knowing that here, then for each element, each element decide if it's in or out. So there's two choices each, right? Given 2 to the n subsets, right? In or out, so that means that here, 2 choices, then we have here 2 to the n subsets. All right, is in or out. All right, that's where our 2 comes in, and there being n elements, so it's either in or out, and that counts the same set the 2 ways. So the sum, And this is our argument, our combinatorial argument. So knowing that they count the same thing, then we can say, all right, then if they count the same thing, then they are indeed equal to each other. Right? And that is the proof. Right? I think here the skill that we need to focus on is to ask the right counting question. Right? If we ask the right counting question, now we can move forward in solving it in the appropriate manner.